Yeah, it's been a while since I brought my laptop to campus, but oh well. Whew. All right. Have a good weekend. Yep. See you next week. I got my laptop working right after I sent the email. It was gonna be virtual. I'm like, of course it did. Well, it's kind of an online thing anyway.
Yeah.
Yes.
Like at least. Just doing meshing.
We're doing meshing and setting up the simulation. We'll be able to run actually a pretty simple simulation from here on your computers, but for the bigger one, you need to use the supercomputer for that. But simple ones you can run here. Yeah, yeah. She's always so surprised whenever she comes.
Everyone.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everybody. So I know I just sent the email, said today's lecture be virtual, but literally right after I sent that email, the Wi-Fi started working on my laptop. So, that's how it is. You got to complain sometimes, and then things will work on you after you complain. So, so I'm here in the classroom, but if you're on Zoom following along, that's fine too. So today the plan is we're going to do a SimVascular workshop, and so. You guys have finished your midterm project at this point. Everyone has their project geometries. You guys did really good. So I graded all of the midterm projects yesterday. So you should, hopefully you should see your grade and the feedback that I gave you online. So that's all good. So the next step is to mesh your model and to run the simulations on it. So that's what we're going to be doing today. So depending on how long today takes, honestly, for this class, I don't have too much more planned for this class for the rest of the semester. So if the workshop today takes two lectures, that's fine too. Of course, we have our midterm exam next Tuesday, and so we definitely need to we'll take a break for that as just to take that midterm exam. But if we need to finish up this workshop next Thursday, then that's fine with me as well. Okay. Because the meshing part isn't too difficult. Well, in theory, it's not too difficult. For you guys, there might be some issues with the meshing. But there is quite a lot to explain with the boundary conditions and the simulation settings, as well as kind of being, I know we went over the project, specifications last time, but I think a lot of that's going to make a lot more sense today. So I wanted to make sure I spend some time to kind of really talk about kind of exactly what I'm expecting of you guys for the simulations, how to set them up. I think, and most importantly today, I want to make sure I get you guys set up with an account on the supercomputer, so you can run your simulations there as well. Okay. So we have a lot planned today, so we'll get started on it. Actually, announcement first. So I know, so homework, the homework 3 was due last night. I know I said I would post solutions for it, but I left them at my house, and so I will post them tomorrow morning, just so you have that to study for the exam for next week. Okay. All right. Any questions on anything before we get started for today? Okay. All right. And so just like I mentioned, question in the chat. Sorry. Our question, will the lowest assignment be dropped? Yes. Yeah. So the lowest homework assignment will be dropped. That'll be done. That should be done automatically on Canvas. And so whatever your lowest assignment is, going to be dropped. But I definitely highly recommend you do the most recent homework assignment, because it is a big part of the exam next week. So you should definitely at least know how to do those problems. Okay. All right. Any other questions about the exam or the project or anything before we get started for today? Yeah.
As far as like the conceptuals go, like on the study guide, like how many would that go should we expect on that?
There'll be five conceptual problems. Yeah. The emphasis will definitely be on the newer stuff, but then you can expect maybe 1 or 2 questions from some of the older stuff. So I definitely place more emphasis on the newer stuff, and then just because it's a lot of stuff, and so I don't want you guys to study a whole semester's worth of stuff. So I'm trying to be upfront, just tell you it's mostly on the newer stuff.
Will it be like one out of the list, or is it like based on like?
It'll be based on it, so it's not going to be exactly, but if you can answer everything on that list, then you're cool. Yeah. Mm-hmm. Yeah. Yes. Yeah. It's it's a short answer question, so 2, 3, 4 sentences, or drawing a figure. Yeah. Mm-hmm. All right. Any other questions? Okay. All right. So let's get started. So like I mentioned in my announcement, I'm going to be working on this project to do the tutorial today, just so I have something to show you. It's also the most stable project, so I know it'll work. And so if you guys want to follow along exactly what I'm doing, you can use the demo project. Or the other option that you have is that you can use your own project and follow along. The only thing is that you guys might have some trouble with the meshing on your project. But if you can get the mesh to work today, you're going to be in fantastic shape. That's we're going to do most of the stuff today. Okay, so after the midterm project, up until the end of the midterm project, you guys should be here. So you guys should have a geometric model of your vessels. Okay. The only thing that you have to do before we move on to the meshing is you have to make sure that all of your segmentations are lofted together in a single model. So most of you guys did that for the midterm project, so that's good. But I did notice for a lot of your midterm projects, you had kind of several different models where each model was a separate vessel. You need to make sure you combine all of it into the same model like this, right? So you can see here that I have one model here that has both the aorta and the right iliac together, okay? Because I know for some of you, if you try to loft it all together, and I tried doing that for your midterm projects too, it did kind of bring up a few issues with like partially intersecting vessels. So you want to make sure that you kind of take care of that, okay? But for this tutorial, we're just going to go ahead and go with this one here. Okay. All right. So first thing I'm actually going to show you is I'm going to show you how to smooth the model. So one thing that you guys will notice is that the next step with the meshing, some of you may have some trouble doing that just because there are a lot of sharp surfaces on your model. It's something I've kind of brought up every now and then throughout the class as well. So first thing we're going to do is we're going to learn how to smooth the model itself. Actually, let me start with the new model just so I can show you. So I'll call it test 2. Okay. So test 2, let me go ahead and re-loft it together from these vessels here. So you notice here I'm putting a check mark on every vessel that I have here, which is just 2. Okay. I'm going to hit OK. Okay, so here is my model here, right? Okay, so if you notice this model for the most part is pretty clean, but if you look at kind of the intersections between the vessels here, so you can see we have this branching vessel that comes off. We have this a little bit of a hard edge that kind of comes around like this, right? And so you can see it's kind of kind of a sharp edge like that. And whenever you have a branching vessel, that's kind of unavoidable, and so you're always going to have some kind of sharp edges like that. But sometimes, it can cause some issues with the meshing. And so first thing we're going to do is we're going to try to smooth out this entire thing to try to make it a little bit easier for our meshing. Where did test 2 come from? So I created a new model from it. So I right-clicked on model. I clicked on create model. And then I just gave it a new name. So I just called it test 2. Yeah. So it's identical to the demo one, but then, I just wanted to show you kind of where I got it from. Okay. So let's see how to smooth this thing. So first of all, if you loft your entire model as one, you'll notice that on the right here, you have a list of all the surfaces in our model, right? So if you click on a surface, you'll see. Oh, question? Yes. Yeah. Yeah. Mm-hmm. Yeah, so from your surfaces list here, if you click on them, you'll notice that it'll highlight the appropriate surface, okay? So you can see we have the wall surfaces and the caps, right? So the caps are kind of the ends of the vessels here, okay? And the walls are the lateral surfaces, right? So the caps we actually don't want to smooth. The caps are already fine as they are. What we actually want to smooth are the walls, okay? And in fact, for the most part, it's the intersection between different walls that needs some smoothing, right? So what I'm going to do, I'm going to hold Control on my keyboard and highlight both of the walls, okay? And so for you guys, if you have more than 2 vessels, you're going to have way more walls than this. So go ahead and highlight all of them, okay? And what I want to do here is I want to smooth this out, okay? All right. And so with both of the walls highlighted, you're going to go to the right-hand side of the screen right here, and you're going to see that there is an option for local ops, okay? So you're going to go down here, click on this button for local ops. Okay. And what this basically means is that we're going to perform some smoothing operations locally just based on the surfaces that we've highlighted, okay? All right, so the one that we want to actually use is this one called Constrain Smooth. Okay, so after you click local ops, there's going to be an option that comes up for Constrain Smooth. So go ahead and click that. Okay. So this window will pop up where it'll ask you to choose some parameters for the Constrain Smooth. For the most part, you can just kind of leave that alone. I wouldn't change those things. And then you're going to click on the button for Smooth and Local. Okay. So you want to make sure that you highlight all the wall surfaces before you do that. So let's go click on Smooth and Local. Okay. It's going to take a little bit of time, but then after you click on that, you should see that this intersection between these vessels, it got smooth a little bit, right? So it's not perfect yet, but it's kind of getting there. So you can click on Smooth Local a few times, and each time that you click it, you should see that the intersection between these 2 vessels starts to improve a bit. Okay. You can see that it's kind of adding some additional volume into this gap here to kind of make it not such like a hard transition. Okay. It's going to look a little bit strange at first, but if you hit smooth local a few times, it's going to smooth it over, right? And so you can see actually up here, I don't know if you remember from before we started, up here there was kind of a hard edge, but you can see that it's kind of perfectly blended together like that. Okay. All right, so we don't have to go too crazy, but just try to smooth it as best as you can. And for those of you, I think I made some comments about how your vessel surfaces were a little bit rough. This is going to help a little bit with that as well. Okay. All right, so maybe I'll do a couple more times. Okay, so that right there is pretty good. Okay, so you can see here that we've added. It almost looks like a little bit of a paste kind of in between to make sure that that transition between the vessels is smooth. Okay, so now that our surface here is a lot smoother, it's going to make our meshing a lot more easy to do. Any questions on this part here? Okay. Okay, so now that our model is smooth, we're all set for meshing. Okay. All right, so let me bring back the project specifications here. And you can see here that the meshing, what we're basically going to do is we're going to replace our model with a collection of a lot of little tiny shapes that are all kind of fitted together. Okay. Okay, so let me go ahead and right click on mesh here. We're going to click on create mesh. Okay, and so it's going to ask you which model that you want to select for this. And so I have two actually right now, just because I made the smooth one. But you want to make sure you choose the model that has all of your segmentations in one. Okay. All right, so you can give your mesh a name. If you don't give it a name, it's going to use the same name as the model. So I think that's fine for me. So I'm just going to hit OK. All right, and so it's going to create an entry under meshes right here, right? And so conveniently, I've given it the same name as my model. Okay. So if you've taken finite elements before with me, or if you're in CFD, you probably kind of know what's going to happen in this step. We need to kind of replace this with a mesh. Okay. The difference here between this and ANSYS is that this doesn't work nearly as well as ANSYS, and so you might have some issues, creating this mesh. Okay? All right. So the main thing that you have to specify for this mesh here is the size of the elements. Okay, and so that is this entry right here. Now, if you're not sure what to pick for the element size, there is an estimate button. And so if you click on the estimate button, it'll fill in a size for you. Okay. And so for this particular model, just because I've done a really good job smoothing it, it's estimated a size of 0.2, basically 0.2, right? 0.2007, right? Now for your models, it may give you a different number, but you want to be careful here because sometimes the way this estimate button works is that it looks at your model and it finds the smallest surface, right? So whether that be a cap, most likely it's a cap, or for those of you who have some partially intersecting vessels, it may be kind of that kind of small sliver of vessel that's kind of peeking out, and then it chooses an element size based on the area of that cap, right? So this is why I kind of really emphasize that you make sure your vessels intersect properly, because if you have a really small surface sticking out, you're going to end up with an estimate mesh size of like 0.0001 like this. Okay. And you don't want to run the mesher with a size like this, because this will crash your computer, because it's going to try to make a mesh with like, probably like 500 million elements, and there's not going to be enough memory to do that. Okay. So you want to be careful. So the estimate button works well if it produces a number like this, but if it produces a really small number, you want to be careful before you hit the run mesher, just because you want to make sure that you don't crash your computer. Okay. Okay. Question. Yes.
If the partially intersecting like caps are only like exterior caps, is that like fine?
So if it's wait, what do you mean exterior caps?
Like mine comes up that I have like partially intersecting vessels on the caps, but they're caps that like don't intersect with any of the vessel.
Oh, I see. So you do want to make sure that your entire model is kind of one, and so you have a vessel that's kind of off on its own, then you have to kind of connect it back in. The SimVascular will give you that warning if you have multiple inlets as well. So I don't remember. I think your model does have multiple inlets, and so you may be getting that error because of that. But otherwise, I think it checks to see if this vessel right here were kind of sticking out a little bit, then it's going to give you an error for that as well.
not like at connection points, they're like at like, I guess like.
The ends of the vessels. Okay, that's fine then. I think it's because your model has multiple inlets, so that's fine. Okay. So when you're ready with the mesh size, and by the way, so the estimate mesh size, this is only just an estimate. And so even if it's giving you something really small, like 0.001, you could increase this as well. So you can actually increase it to, maybe 0.1. The mesher may give you an error if you do so, but it's at least a starting point. Okay, so I'm going to go ahead and run with this mesh, and in fact, I'm going to keep all the rest of the settings the same. So I'm going to go ahead and click Run Mesher and pray to Jesus that this works. Usually not a good sign. My laptop was crying just now because it's trying to run Zoom and SimVascular at the same time. So it's like I have no more RAM. Good, it worked. Okay. So if your mesh was successful, you should get a box that comes up that gives you the mesh statistics. Okay. And so it gives you a nice little congratulations. It says mesh done. Congrats. Here are the statistics. Okay. And so the number one thing that you have to pay attention to your mesh is the number of elements right here. Okay. So you can see for this mesh that I have right now, I have about 260,000 elements. So 258, 241. Okay. This is a fairly light mesh, and so this is actually a mesh that I'm going to run the simulation on this computer. But for your guys's projects, you should aim for a mesh of around either 500, at least 500,000 elements, maybe even up to 1 million or 2 million. Okay. So I'm going to run with a fairly light mesh for today, just because I want to show you the simulations. But this mesh density is not really suitable enough for an accurate simulation. So depending on your model, so some of the bigger models. So for those of you doing aorta models, I think you should be closer to 2 million elements. For those of you doing the smaller models like the pulmonaries or the congenital heart disease, you can probably be closer to 500,000. Okay. But again, for today, I'm just running with the coarse mesh just to show you. Okay, so you can go ahead and click OK. And if you ever forget how many elements were in your mesh, or you close that window too quickly, you can click on this mesh info button, and that'll give you the same number of elements as well. Okay. And so if I turn off the model itself, you can kind of visually see the mesh, and so you can see all the little triangles that have broke up this mesh in. Okay. So for those of you who have taken my finite elements, you don't really have an option for the shape. The only shape that is available is tetrahedrons, and so that's why the surface is triangular. Okay. So I'm going to go ahead and roll with this for today. And if you're working on your own model, if you're able to get a mesh from today, that's fantastic. That's probably the hardest part that you have to do. Any questions on the meshing? Yes.
So how would we get
higher number of elements?
Yeah, like really low.
Yeah, so if you want to increase the number of elements, you just decrease the size here. And so this size here that you're specifying is the size of each of these. It's basically the edge size for this one. And so if you make the elements smaller, it's going to increase the number of elements. So I'll show you. So if we change this to 0.1 instead of 0.2, I'm going to end up with probably roughly around a million elements if my computer doesn't crash. Yeah, those of you with aorta models, I think probably you probably shouldn't have too much trouble meshing, but you want to make sure that your element count is on the higher side. Yeah.
So,
Yeah, it depends on your model geometry. So because I know a lot of people doing aorta models, aorta femoral models, I think you should be at least north of 1 million. But for those doing pulmonary models, so those are models with kind of smaller geometries. Pulmonary, cerebrovascular, I think you can be closer to 500,000. I think that's okay. Yeah, yeah. Mm-hmm. Yeah, so you can see when you decrease the element size, it does take longer for the mesh to generate. So just kind of be aware of that. Yeah.
I have a question about like the smoothing.
Yeah.
Like in this case, it's only like two vessels, but like for ours, if we give it to like, so like every single wall.
Yep.
At the same time.
Yep. Yep. In fact, that's what you should do, because it kind of smooths it all kind of all together. Yeah. Yeah. I mean, you can see. So I mean, when you run your simulation, you'll be able to tell kind of how accurate it is. I think yours was a aorta model. I think it was. I think you should be north of 1 million. And so I think yeah. For today, I would keep the element count lower, just because we're actually gonna run the simulations on the desktop. But for your project, and you're gonna run it on the supercomputer, I would be north of 1 million. Yeah. Yeah, so you can see that after I refined the mesh, my element count now is above 2 million. So this would be a good element count for a model like this, if I were running this on the supercomputer. But I'm not. I'm running this on my desktop, so I'm gonna put this back to 0.2. You can see my computer's dying. I'm using up 1 gigabyte of memory right now. All right. Yeah, there are a lot of other meshing settings here, and you can play around with these if you want. But if you want to just be simple, I would just use the default settings. All right, any other questions on the mesh here? Yeah. To decrease the number of elements, you would increase the size here. Yeah. So there's kind of an inverse relationship between the size and the number of elements in the mesh. Yeah. You can think of this element size as almost kind of like the resolution on like a digital image. And so kind of the smaller your pixels are, the more sharp your images. Questions in the chat? Question: when we have to smooth our models, we have to click every vessel, or so the measure will be done on the supercomputer? No, you're going to do the meshing on your local computer, but the simulation will be done on the supercomputer. Yeah. When you're smoothing your models, you want to select just the wall surfaces. And so when you the smoothing is done from the model tab over here. So you want to make sure you just highlight the walls. You don't want to smooth the caps, because the caps are already fine. You want to just make sure you smooth the walls. Yeah. Okay. All right. Any other questions on this step here? Okay. Yeah. If your mesh element size is too small, you could be waiting up to an hour for your mesh. And so if you've been waiting more than 15-20 minutes for your mesh, you should maybe think about just killing it, and then maybe trying with the bigger size. Yeah. So close SimVascular, open it again. Maybe restart your computer to clear the cache. And so yeah, you want to be careful with the meshing. Okay, so with your mesh complete, we're now ready to move on to the simulation. Okay. Okay, so to create a new simulation job, you can right-click on simulations here and click on create simulation job, right? So under the simulation job, that's where we're going to be able to specify all of our boundary conditions and all of our simulation settings for our simulation. Okay. Okay. So once again, it's going to ask you to select a model. So I'm going to go ahead and select test 2, because that's the one that I created a mesh for. Okay. And we'll have to give it a name. So I'm going to give it test simulation. Or let me call it, I'll call it test simulation. That's fine. Okay. So after you create a new simulation job, it's going to create something under here. So go ahead and double click on test simulation. And so from here, we're going to be basically working on all of this, all of these settings over here. A lot of these settings here, we're going to skip over just because we're going to work on the defaults, but there are some really important ones that we have to do. Okay, so with the test simulation checked, we are now ready to kind of move on over here. So first thing we're going to select here are the basic parameters. So things like the fluid density, the fluid viscosity, any initial conditions that we may have, right? So for you guys, we didn't really make any changes to the units, and so we're using kind of the default ones. And so you can leave the fluid density and fluid viscosity alone. So these values are perfectly fine for the simulation. Okay, so the next tab that we're going to go down to is the inlet and outlet boundary conditions. So here we're gonna spend a bit of time. Okay, so if you remember on Tuesday, we talked about the boundary conditions and we talked about their importance, right? So we need to specify which caps on our model are going to be our inlets, which caps on our model are going to be our outlets, and that's going to specify the direction of flow in our model. Okay. All right, and so every model is a little bit different. And so if you're not sure which caps on your model are going to be your inlets and which ones are going to be your outlets, definitely shoot me an email or just ask me. I can let you know. But for all of the aorta models, your inlet is almost always going to be the inlet of the aorta. Okay. So for this model right here is an aorta femoral model. So my inlet is at the top. But for a lot of you guys, I know you have an aorta model, so it kind of arcs like this, right? And so for you guys, your inlet is going to be this cap right here. Okay. And most of your models are single inlet models. And so everything that's not an inlet is going to be an outlet. Okay. All right. But for this model, I know that the inlet is going to be on cap aorta. Okay. And so let's click on cap aorta here. And so when you click on the surface, it highlights it in the model. So I know that I'm in the right one here. Okay. So with cap aorta highlighted, we need to choose its boundary condition type. And so the boundary condition type for this one, if you double click on this box here, it's going to give you some options. And so the first option is called prescribed velocities. The second option is resistance. The third is RCR, and the fourth is called coronary. Okay. For this project, we're only going to concern ourselves with the first two types of boundary conditions, but you can also explore the other ones if you want as well. Okay. So for our inlet cap, right? So for our inlet model, the type of boundary condition we want to specify there is prescribed velocities. So we want to make sure we click that. Okay. All right. So the next thing is we need to specify its value. So to specify the values, we're actually going to double click on cap aorta here. Okay. Make sure you've already selected prescribed velocity as the type, and then after you double click on cap aorta, this new box is going to come up. Okay. Okay. So from here, we need to specify the settings for our cap aorta here. Okay. The first thing we're going to choose here is the shape of the profile. Okay. So we have three options for the shape here. We have a parabolic shape, we have a plug shape, and a Wormersley shape. Okay. So if you remember from our lectures from last week, you should remember kind of what the Wormersley profile looks like. Okay. And so if you're doing an unsteady simulation, you should pick the Wormersley profile. Otherwise, you should pick parabolic or plug. Okay. Doesn't really matter which one you pick between those ones. For this one, I'm going to pick parabolic just because that's the default option. These next two options here, we're going to select the point number and the Fourier modes. Okay. So if you remember from last week, we discussed Fourier modes kind of briefly, and what that means for the model. I'm just going to leave this as the default for 10. That's fine. All right. And so the next thing we need to upload here is what's called a flow rate file. Okay. So actually, if you go to Canvas, and actually I can't open it because my computer is out of memory. But if you go on Canvas, you'll see that I've uploaded an additional file under week 13. Okay. So actually, let me bring it up here. Oops, not here. Actually, I have it on the desktop. Okay, so if you go on Canvas, you'll see that I've uploaded an additional file called capaorta.flow. Okay, and so if you double click on that file, you'll see that it's just a simple text file. And if it's asking you what program to open it in, you can just open it up in Notepad. It's just a simple text file. Okay, and what you're seeing here is the flow rate of this model as a function of time. Right. So the way to read this is that it's a two-column data structure. Okay, so the first column here is time. And the second column here is flow. Okay. So that means that when t is equal to 0 seconds, that means our flow rate into the cap is going to be a minus 100 milliliters per second. That is the units for that. Okay. And then when t is equal to 1 second, then our flow rate is going to be a minus 100 milliliters per second. Okay. Notice that is constant. And so for this particular job here, we're going to run this is a steady simulation. Okay. It's a steady state simulation because the flow rate at the inlet is not changing. Okay. It is possible to do a pulsatile simulation, and the way you do a pulsatile simulation is that you upload another flow file to this here. Okay. I did upload a pulsatile flow rate file to Canvas as well, but for now we'll just select the steady one. Okay. All right, so I'm going to go ahead and search for that file. So for me, it's already kind of built into the project, but for you guys, you can download it and upload it from there. Okay. So let me go here. Okay. And so make sure you highlight cap aorta flow. I'm just going to double click that. Okay. And then once you upload that, it should automatically determine the period from there. Okay. All right, so then I'm going to go ahead and click OK. Right. And then after you click OK, it's going to say that your inlet boundary condition has been assigned. Okay. All right, any questions on that? Yeah. Yes. Yeah, you download it from Canvas and then you load it into the software. Mm-hmm. Right. Any other questions on this part here? Okay. All right. So next we have the outlet boundary conditions. And so for the outlet boundary conditions, for all your outlets, you're going to choose a resistance type boundary condition. Okay. So if you think back to our lump parameter unit, you'll know that a resistance basically means that there's a relationship between flow and pressure, right? Because we know from Ohm's law that we have pressure is equal to flow rate Q multiplied by the resistance. Okay. And so a resistance boundary condition just basically states that whatever flow rate is coming out of that vessel, we're going to multiply that by the resistance, and then that's going to give us our pressure boundary condition. Okay. And so what we need to specify for these resistance boundary conditions is the value of R, or the value of resistance for each of the outlets. Okay. Okay. And so for that, the way you compute that is actually you need a formula for that. Okay. So if you go back to the project specifications, you'll see that I have this formula here for you. Okay. And so basically this formula is total peripheral resistance, or PVR, is equal to the target mean pressure, or the average pressure in your model, divided by the inlet flow rate. Okay. And you want to make sure that it's in these units. Okay. And if you examine this formula, you can see here that the resistance, you just plug in values for it. The resistance is equal to pressure divided by flow rate. Okay. So this equation here is nothing more than just our usual resistance equation. It's just that we've kind of flipped it to solve for the resistance itself. Okay. Okay. So for this part here, you need to make sure that you use appropriate units or appropriate values for your specific patient. Okay. So for all your projects, I've uploaded that PDF document for you guys. That PDF document should have some information about the average flow and the average pressure for your patient. Okay. And so we want to make sure that we use that information here, right? The important thing for the pressure is that you want to make sure that the pressure is given in terms of dyne per centimeter squared. Okay. Okay. But for the most part, most pressures are going to be given to you in terms of millimeter mercury, right? And so for this patient, I know that the average pressure is 93 millimeter mercury. Okay. And so to convert it to dyne per centimeter square, we need to multiply it by a conversion factor. Okay. And so the conversion factor to go from millimeter mercury to dyne per centimeter squared is approximately 1,333. Okay. It's a little bit different than that. It's like 1,334 point something, but I just like to remember 1,333. Okay. Okay, and then we're going to divide that by the inlet flow rate. And so if you recall from our flow file, our inlet flow rate is 100 milliliters per second. Okay. And so if we punch this into a calculator, let me go ahead and pull one out here. Calculator. Okay. So I'm going to do 93 times 1,333 divided by 100. Okay. We get a total vascular resistance of about 1,240. Okay. So this right here is our total resistance. Okay. So let's hang on to this number. So let's kind of remember this this number right here. Okay. So that means in total, right? For every outlet in our model, their total resistance is going to be about 1,240. Okay. Now, that represents the total resistance of every outlet in our model. But in order to specify our boundary conditions, we need to specify an individual resistance. Okay. So we basically need to do kind of the opposite of what we usually do. So right now, what we have is that we have the value for a single resistor is 1240. Okay. But we need to convert this so that if we have two outlets, and usually for every outlet, we assume that they are in parallel. Okay. Right? Remember, usually we go the other way. Usually we go from two resistors in parallel to one lump resistance. Okay. This time we're going the opposite. So we're going from one lump resistance and we're splitting it. We're splitting it among all the different outlets like this. Okay. All right. So luckily for us, SimVascular actually has a way to kind of do this operation for you. The only information that you have to give it is this value right here. Okay. Okay. So to do that, we're going to highlight all the caps in our model here that have a resistance outlet. So for this tutorial, was just two of these caps. Okay. So with both of these highlighted, I'm going to right click on them. And then after you right click, there's going to be an option that comes up for split resistance. Okay. So I'm going to go ahead and click on split resistance. And after you click on split resistance, this new window is going to pop up. Okay. It's going to ask you for two pieces of information. So the first information that's going to ask you for is the total resistance. And so that's where we're going to input that number there. Okay. So that's the one we just computed, 1240. And the next thing it's going to ask you for is the Murray's Law coefficient. So if you remember from kind of very early on in the semester, Murray's Law kind of tells us kind of the relationship between daughter vessel and parent vessels. Okay. And so here it's actually used to kind of help split our resistances. So for an aorta like this, I would say the Murray's Law coefficient is probably around 2.2 or 2.3. Okay. So depending on where your model is or what the geometry for your model is, you may input a different Murray's Law coefficient. But usually anywhere between 2 and 3 is usually pretty reasonable. Okay. Yes, question.
Is that coefficient from like that one you showed it?
Yes. Yeah. So it depends on the size of your vessels. For aorta models, I would say 2.2, 2.3 is pretty reasonable. For smaller models like pulmonaries and cerebrovascular, I'd probably say maybe like 2.5, 2.6 is pretty good. If you're doing congenital heart models, I would say probably closer to 2.3, probably be pretty good. Yeah. And so if you have questions on that, just let me know. We'll pick. Okay, so I'm going to pick 2.3 for this, and so I'm going to hit OK. And then after you do that, you can see that it's split the resistances for me, right? And so the resistance for cap iliac, which is this one right here, is 2,212, and the resistance for cap aorta is 2,820. Okay. The resistances that you should get here should be higher than your total resistance, because remember, we're splitting them in parallel, right? And so when you split things in parallel, they have to go up in value in order to kind of maintain the same total resistance. Okay. All right, so that was a lot of information. So this is probably the most important part of your simulation, making sure you get the inlet and outlet boundary conditions correct. Any questions on this part here? Okay, good. Let me go ahead and clear this. All right, so the next thing that we're going to do here is we're going to set the wall properties. Okay, so the wall properties are how the wall here is going to deform or not. Okay. So the default configuration is to have rigid walls, which is basically to make sure the walls don't move at all. Okay. So for your guys' projects, you can just run with rigid wall simulations. That's totally fine. If you wanted to, you can try to run the simulation with deformable walls. And so if you're going to run a deformable wall simulation, you need to specify the thickness of the walls, the elastic modulus, the density, as well as the reference pressure as well. Okay. So that reference pressure is used as part of the constitutive model. But deformable wall simulations are a lot more difficult to run. And honestly, I would just stick to rigid for now. And so if you're interested in doing deformable wall simulations, we can maybe do that at the end. But I would stick to just kind of rigid simulations for me. Okay. So the next part of the project here is we're going to set the solver parameters. Okay. So the solver parameters, these are kind of everything else that we need to specify to run our simulation. Okay. So the first two things that we need to specify here are the number of time steps and the time step size, right? So remember, we talked about this on Tuesday as being important parts of a CFD simulation. Okay. So the first thing I would specify actually is the time step size. So remember, this is the amount of time that it elapses in between each time step. So generally, you know, for most cardiovascular simulations, I would say, you know, 1 millisecond is a pretty good time step size. You want it to be small enough so that your simulation is accurate, but not so small that your simulation becomes too expensive. Okay, so there's a balance with this, just like with the mesh density. Okay? But generally speaking, 1 millisecond is usually pretty good for most people. Okay? And the number of time steps, this is going to tell us, you know, how long or how many time steps we're going to run our simulation. Okay. Normally, I would do something like 1,000 here. Okay. Because if you simulate for 1,000 time steps and there's, you know, 1 millisecond in between each time step, that means we'd be simulating kind of 1 second of blood flow. Okay. But for a steady simulation, you know, 1,000 steps is a little bit overkill. And so since I know the simulation is going to be steady, I would set the number of time steps to 100. Okay. But for your pulsatile simulations, the ones where you're going to have unsteady boundary conditions, I would set the number of time steps to be about 6,000. Okay. So that you run 6 kind of full cycles. Right? But for now, I'm just going to keep it at 100, just so I can finish it. Okay, next thing that we're going to specify here is the number of time steps between restarts. So remember, we talked about this on Tuesday as well. This specifies how often your solver is going to save results, right? So you don't want to save your simulation results every time step, because that's going to overload your computer. It's going to cost too much memory. So for this simulation, I'm saving about every 10 time steps. Okay, so that gives us 10 data points to look at, which is fine. Okay. So besides that, you know, most of these other things we're going to keep the same. We're going to make a few changes to the linear solver just to make it run a bit better. Okay. So for these ones, you know, I don't want to get into kind of the theory behind these just because it'll kind of take too long. If you're taking CFD, you probably will know kind of what some of these are, but you know, for now, I would just say, just trust me. Okay. So the step construction tells us basically how often we're going to iterate for our linear solver. So I would change that from 2 to 5 in general. Next thing we're going to specify here is the residual criteria. So the default for this is 0.01. So I'm going to add one more 0 to this, and so it's going to be 0.001. Okay. All right, and then the last thing we're going to specify here are the tolerances on our linear solver. Okay, and so the defaults here are often kind of way too large. So I want to make these a bit smaller. So for each of these, I'm gonna set them to match the residual criteria. So I'm going to set them to be 0.001. 0.001 and 0.001. Okay. So that's lines 23, 24, 25. I'm going to set all of those tolerances to be 0.001. Okay. And that's just to make sure that the linear solver kind of works hard enough to get us a solution. Okay, so the last thing I'm going to change here is the line 26. And so this is another kind of iteration thing. And so instead of 1, I'm going to change this to 10. Okay. Just to kind of make sure that this all kind of finishes okay. Okay, so just to kind of summarize everything that I changed here, I changed line 11. Okay, so line 11 I changed from 2 to 5. I changed line 17, and so line 17 I changed from 0.01 to 0.001. I changed lines 23, 24, and 25. Okay, same thing. So I want to make sure that all of our tolerances are at 0.001. And then the last thing I changed was line 26, which was the number of iterations, which I changed that from 1 to 10. Okay. All right. Any questions on that? Okay. Good. Okay. So now that all of our solver parameters are specified here, we are ready to run the simulation. And so the next tab that you're going to go into is this one: create files and run simulation. Okay. All right. So here on this tab here, you know, we've basically specified all our boundary conditions, all of our solver parameters, and so The first thing we need to do is to run what's called the pre-solver. And so the pre-solver is a program that's used to create just the inputs for the simulation. Okay? So to run the pre-solver, you need to select a mesh here. For those of you who are following along, you may not have the pre-solver installed, so I'll walk you through that in a second. Okay. So make sure you choose the right mesh, and so you choose the mesh that you want to use for the simulation, and then you're going to click on this button right here for Create Data Files for Simulation. Okay. So if you don't have the pre-solver installed, it's going to give you an error here that says you need to install the pre-solver, but I'll walk through that in a second. Okay. But if you do have the pre-solver installed, then it's going to say that your data files have been created. You can see some details here. Okay. Right. Now at this step right here, if you wanted to run your simulation on the cluster, you would stop right here. So you wouldn't continue. Okay. And then from here, what you would do is that you would take your simulation files and then you would upload that to the cluster itself. Okay. Okay. But for now, because this simulation, the mesh only had 250,000 elements, I'm going to go ahead and run this on my computer. So I'm going to go ahead and click Run Simulation. Okay. And then the simulation should start running. And so if you're running your simulation on your desktop, you can see the progress for the simulation in the bottom left-hand side of the screen. Okay. So this actually might take a while just because my computer is kind of gasping for breath right now. So I don't know how long this is going to take, but maybe around 5-10 minutes, I think, with the 250,000 mesh. Okay. Any questions? Yes. No. So you said SolidWorks? No. So you don't need SolidWorks, but you do need to install the SV solver, the SimVascular solver. So while that's running, actually, let me show you how to install it. Okay, so if you don't have the SV solver installed, here's how you install it. Okay. So you're going to go ahead and go to www.simvascular.org. It's going to say that it's not private, but that's okay. Oops. Or maybe we'll search SimVascular. Okay. Okay, I'm sorry. The website is simvascular.github.io. Okay. Okay, so basically this is the same place that you went to download SimVascular to begin with. So you're going to go to download. Okay. You're going to download the installation package. Okay. So this is going to take you to simtk.org. So this is the website that we used to download. So before you guys downloaded this version of SimVascular right here. Okay. Now that you are running simulations, the one that you want to download now is called SV Solver, which is this one right here. Okay. Okay. So with SV Solver, and be careful, you don't want SV1D Solver, you just want regular SV Solver. Okay. Okay, so you're going to click on download links, and you're going to click on the link for your operating system. So for most of you guys, it's either going to be Windows or Mac. Okay. And then you just kind of follow the instructions on screen there to install the solver. Yeah.
Is there a way to run simulation in a laptop with multiple?
Yes. Yeah. So actually, if you install the solver, I think it's going to ask you if you want to install MPI as well. And so when you run the simulation, it's going to say there's a checkbox here for use MPI, and then you can increase the number of cores. Oh yeah, yeah, yeah. Just be careful though. If you're going to run multiple cores, it is going to overload your machine. So make sure you're not doing anything, not gaming or anything during that time, because your laptop might blow up. I see. Oh, cool. Yeah, so SimVascular does that automatically for you. So it decomposes it based on the number of processors. Yeah. All right. So I don't think this is finishing. I think I don't have enough RAM. I'm trying to run Zoom and Chrome and SimVascular at the same time. So this is probably not going to finish today, but that's okay. But that's how you run simulations. Any questions on just kind of the whole process that we went through today? Okay. Okay. I might actually kill this, but before I go, let me show you how to actually sign up for the gateway. We actually finished a lot sooner than I thought. Okay, so you can see that even for a mesh of 250,000, it's pretty hard on my laptop. And granted, my laptop is over 6 years old, so it is getting up there in years. So your laptops may have a better chance with this. But once you get a mesh that's like 500,000 elements, 1 million elements, 2 million elements, that kind of becomes impossible to run on your home computer. Okay, so to run jobs on the cluster, you're going to open up a web browser. You're going to go to www.gateway, or I should say, you're going to go to gateway.simvascular.org. I'll send an announcement through the class with information about this too. Okay. And so you can see this website. Obviously, I did not ask my wife to help me design this because it's really ugly. I'm aware of that. But this is our gateway website. Okay. So what you're going to do is you're going to create an account. Okay. You're going to click on create account here. So for all of you, because you have already an account with Cal State Fullerton, we can use your Cal State Fullerton account to make your gateway account. So you're going to click on this button here for sign in with existing institution credentials. Okay. And then for me, it's already kind of hotkey to go to Cal State Fullerton. But on the next page, you should see a website where it says you can select your institution and you can select Cal State Fullerton from that list. Okay. So you're going to create your account. You're going to log in with your Cal State Fullerton ID. Okay. Okay. So for me, it kind of already loads the gateway for me. But for you guys, you're going to have to go through the account creation process. When you first make your account, you're not going to be able to run simulations because you have to get approval from the mod, which is me. Okay. So what I'm going to be doing, so unfortunately we haven't automated it, so I do have to go in and manually kind of approve your accounts. So if you guys can make your accounts over the next couple of days, what I'll do early next week is I'll go in and approve all the accounts. Basically, I'm just going to search for everyone with the Fullerton email address and just approve all of it. Okay. But before we do that, let me go ahead and show you how to actually run a simulation on the gateway. Okay. So to run a simulation here, you would basically click on SimVascular. You can see here we have a few different types of applications here, but the one you want is just SimVascular. Okay. And what you're going to need to do is you need to upload all of your simulation files. Okay. Now, if you remember just from 10 minutes ago when we were doing this part here, there was a part where we clicked on create data files for simulation. Okay. If you go through your Windows Explorer and you go to the folder, so if you go to your project folder, you go under simulations, right? So here's your SimVascular project folder. You go under simulations here. Okay. You go inside the folder that corresponds to the job that you just created. So I just created this job test simulation. Okay. Right. And so you're going to see a bunch of files here. Right. So what you need to do is you need to upload these specific files to the cluster. Okay. So you need to upload geombc.dat. So I'm going to go quick and drag this onto here. Okay. Right. So that uploaded geombc.dat. We need to upload the restart file. So restart file is restart.0.1. So I'm going to click and drag this here. Okay. Next thing is the DAT file. So the DAT file is this one called bct.dat. So I'm going to click and drag bct onto here. The next file that we need to upload here is the solver input. So there's a text file here called solver that you're going to click and drag right here. Okay. The next one that you need to upload is the numstart file. Now for the numstart file, you have to be careful. So the numstart file is just a simple text file. It's the dumbest file in the world, but this is what you get when you work on a code from the 70s. So when you upload the numstart file, it should just be a blank file that just has the number 0. Okay. You want to make sure that it's 0. So you want to make sure it's not something else. Okay. I'm going to upload numstart.dat. Okay. Okay. And so for you guys are going to be a default gateway user. I'm not going to give you access to my research allocation. And you'll be able to choose, how many processors that you can choose. Okay. So to adjust the number of processors or the number of cores for your simulation, you're going to, adjust this number here, okay? So you can see the default is already pretty high. So the default here is 24 processors, which is huge. Okay? If you remember from our lecture on Tuesday, the way that you choose the number of cores for your simulation is that you take the number of elements in your simulation, or in your mesh, excuse me, and then you divide it by 20,000. Okay. So that'll give you the number of elements that, or the number of processors that you should use. So for my simulation here, the one that I'm running right now, I have about 250,000 elements. Or like 260,000, I guess, 260,000. So if I divide this by 20,000, you can see that those zeros are going to cancel out. And so that gives me about 13 processors. Okay. Okay. So if I were to follow this rule right here for this simulation, I would do 13 processors for that. Okay. Okay. Next thing you're going to specify here is the wall time. So that's how much time that you're going to reserve on the cluster. You can go ahead and max this out. I would just, put this at 1200 minutes. I think that's fine. You want to make sure that you give your simulation enough time to finish. And the cluster that we're using is a pretty modern cluster. So if you don't use all that time, it basically refunds me the difference. And so you can just max that out. I think that's fine. Okay. Okay, so this next part's really important. So for the total physical memory, for this one, you just leave it blank. Okay. So if you leave it blank, what that does is that it allows the cluster to kind of dynamically choose, how many cores you're going to run for the simulation, or how much memory to allocate for it. Okay. And so leaving it blank is actually the best thing, but there are some applications where you want to specify the number of memory beforehand, and so you can do that. But for most cases, you can just leave this blank. Okay. Okay. And so once you're done with that, you can go ahead and run the simulation. So let me go ahead and clear this. So I'm going to go click Save and Launch. And hopefully the cluster isn't too busy right now, so it should be able to run. Okay. And you'll see the big difference, right? So you'll see that so running the simulation on my laptop is only 7% complete right now. So it's definitely not going to finish within the lecture time. But this gateway simulation should finish pretty quickly. Okay, good. It's running already. Okay, any questions on this so far? All right, so for now, we'll just kind of wait for this simulation to finish. I guess we could talk about post-processing today, but I think I'll save that for after the midterm, just because I don't think these simulations are going to finish in time. Okay, all right, so that's everything I had planned for today. So remember, just to recap, today we kind of learned how to create our models, how to smooth them, how to create a mesh, and how to set up a simulation and run it. Okay. So if you want, I would go ahead and try running a simulation on your laptop just to try it out. Make sure the element count isn't too big. So maybe something about 100,000 elements I think will be fine. Just so that you can kind of get some practice with that. And then I would go ahead and make your account on the gateway as well, just so I can approve it. Okay. All right. So thank you guys for coming today. I know it was kind of a lot of information, but hopefully it was useful for you guys. When we come back on Tuesday, we're taking the midterm exam, so make sure you guys are ready for that. I'll be posting solutions for the homeworks tomorrow. And yeah, hope you guys have a good rest of your day. Hope you guys have a good weekend. Yeah, of course. Yeah. Yeah, this recording will be on YouTube just so you can use it for your reference too. Yeah. Sure.
Let's say like the model we didn't get I didn't get a pass. Yeah, let's say like it could have been good. Would you recommend changing the model to like fit your comments?
Yeah, definitely. Yeah, definitely. Just because I think you're gonna have some. I think for your model in particular, you're gonna have some trouble with the meshing, just with the surface is rough.
Yeah,
so I would definitely try to smooth it out.
it seems like when I ran the smoother on it,
Yeah,
kind of like fixed like a lot of
okay,
okay.
good.
Would you like? I'd probably like fix some of those segments a little bit more.
Maybe, yeah. So were you able to get a mesh on it today?
I didn't want to run the mesh just in case I had to change my segments.
Yeah,
but
I maybe give the mesh if you're able to get a mesh with a reasonable amount of elements. I'd say maybe that's okay.
Okay.
But if you're having trouble with the mesh, then I would go back and revise.
Yeah. Thank you.
Yep.
I
No.
looked through it, I just haven't like started it.
I mean, the answers are all in the notes.
Okay, yeah.
Cause I had to. I was thinking of ways.
Oh, God.
Like all this.
Got that.
Someone didn't know that I had. I was able to-
Yeah, that's true. For the calculation I showed you the other day,
Yeah.
I followed your step, it's correct.
Oh, is it?
Yeah.
Okay, good. Okay.
Yeah, so when we start calculate the, just the start of the.
Yeah, yeah.
Okay.
Yeah, yeah. Good.
I had a question because I came in on.
Yeah.
I know I mentioned it sounds like about like this section that's getting about smoothie.
Yeah.
I was trying to find it when we were doing it, but I was supposed to be one of these like, yeah, I couldn't find the simulation.
Yeah, so you want to, first of all, you want to, have all the walls and you're gonna click on all the walls, right? Yeah. So actually, each of these is kind of a different category. Go ahead and highlight right away. Click on local ops. Go to constraints, CS2, and then just click this, click it once just to see. Actually, the computer is fine.
I can't make it.
Yeah, so you can see it's a little bit. So you may have to hit it a few times. So I can see it is a little.
I'm flying down here, so
I think overall your models actually looks really nice. And I don't think we're gonna have too many issues, maybe with RAM, so if your mesh size is too small, I think there just may not be enough memory to hold it all. So I would maybe play with the mesh size, but I think overall your model looked really good too.
Okay.
But yeah, maybe you can probably stretch it a little more. You can see it's kind of helping a little bit. Yeah,
I'll probably run the actual simulation on my.
Yeah, yeah.
School one, so that's like, I didn't want to get gigs of RAM.
yeah, it's gonna be tough. Yeah, so I would smooth it here and then transport the project to your PC and then you can run the mesh.
Okay, for sure.
Yeah.
And then if you ask, but it's, you're gonna put the recording, right?
Yes, of course, of course. Yeah.
So I tried to do the mesh for my model.
Yeah.
Like I have 44 models, but I managed a single one.
Okay.
And then I did the smoothing.
Yep.
But then it's not giving me errors when I'm doing it.
Yeah, so for models like this, it's gonna be tough, even after this. Let me see. I'm gonna time until.
Because I was counting the walls and the gaps.
Yeah.
And I thought the right side was walls and gaps.
I see it's smooth right there. Where's the doing file?
And I try using a bigger number,
Yeah.
but it will give me errors.
Yeah,
Like
yeah.
I try using 0.1. Like it will go fast, but then it will give me an error. And when I try this one, it took like 5 minutes, but still getting an error.
It's tricky. I think your guys' biggest hurdle is gonna be just getting hash. And sometimes it's so hard because I'm wondering, this might be causing the issue right there.
Oh.
Because it's the model's kind of pitching in on itself a little bit. So when the mesher goes in and tries to mesh this, it may not be able to find an element to kind of bridge just yet.
Okay.
Because even though it's supposed to be all one solid model, you can see here there's a really tiny gap because of the pinching. So hopefully sometimes the smoothing is able to take care of that. So you can keep trying to smooth it. Some back here, let me go back here. We can try maybe some of the other smoothing options. The constrained smooth is the most stable one. Because what can happen sometimes with the other smoothing ones is that the volume will actually decrease. So every time you smooth it, like let's say with the Laplacian smooth, it actually kind of shrinks the model a little bit. That's how it's smooth. But if you do it once or twice, it's usually okay, but you definitely don't want to do it another thing that you can do, even though eventually you're gonna have to do it for the full model. Usually it's like one or two vessels that are causing it to fill. And so you can create kind of like test models. You just swap a few vessels and try to mesh that. And then that's usually the most successful. And then usually you'll find one or two vessels where it's like, that's the vessel that's causing it.
Also, maybe I'll try to like.
It does take a while. It is kind of very in that, but sometimes that's kind of the option. Because otherwise, you know, I think you did a really nice job with this, especially, I mean, both of you did a really nice job with this. It's just sometimes, it just twists so much that sometimes you just get some pinching, and sometimes it's just not much you can do well too. I mean, you can just kind of keep trying to smooth it and see. The fact that when I hit the estimated mesh size, I mean, it did end up being pretty small, but it wasn't like astronomically small. That means you did a really good job. It's just the measures was so right here too.
Oh.
Like this model is actually kind of like clipping into itself. So this might be causing an issue too. So you can maybe like try to look through your model just visually and see which vessels are kind of doing stuff like that. Maybe remove them first, and then trying to recreate the model and remesh it. See if that works. Like I would say probably this vessel might be probably an issue.
Somewhere down there.
Yeah, someone.
Like this one?
Yeah. This one doesn't. Yeah, that's probably an issue. Even with the smooth, it's not. Probably a little. Like this part right here, it almost looks like the model's kind of like. Actually, let me try. Let's say this. Before trying to think like you can try some of the other smoothing operations too. The constrained one is the most conservative, but all the other ones are even more aggressive. So decimate is actually a pretty aggressive one. What that actually aims to do is that it actually eliminates some of these surface intercepts. This didn't exist before.
Oh.
It's actually really
This is
good.
good.
Yeah. I would verify to make sure maybe these vessels are the one that's causing the issue. I would even do, you know, in the worst case, I've told people like do one vessel at a time. Make it one model, just one mess with one vessel, mesh it, that works. Then you know, add another one to it. It's a little bit tedious process, but sometimes that's the most but visually, I think you know that that's good. Wherever you see pinching, that's the issue. And there's that one, and then
Someone with.
this one. So yeah, I would look at those and see. What you can do is that if you this is all over the database, but you can artificially kind of smooth this vessel out. And so you know, I know you tried really hard to follow that vessel as closely as you can. But you know what you can do is that you can kind of maybe eliminate one of the segmentation here so that you kind of have a nice smooth thing. So we're kind of getting away a little bit from the accuracy, but you know, for something like this, sometimes you start to lose traffic to get this is going to be the most challenging stuff for you guys. Getting mesh for you. But once you get the meshes, you'll feel the focused. Yeah, it looks really good.
Thank you. So maybe I'll try to do the next for the individual.
Yeah,
nodes
I would try that.
and see if they work or not. So no, okay, I need to notify this and
Yes. Yeah.
names and things.
Yeah.
This is my question.
Okay.
Question.
Sure.
I spent most of the beginning of the class, well, most of this actually, trying just to get it so box. I think it's something like that. And I kind of heard you saying to like do it in segments to see where the shooter is.
Yeah.
Some difference between like Trump and the main. The main is like the main. Or
Yeah.
massive, like this massive section. But like I was looking through the slide, you want them to intersect kind of near the center line point.
Yeah.
Have the cross sections in like within like you want to contain by the other block.
Okay. Yeah. So this is perfect. Right? So a small segmentation. That's
It was, I did just suggest this, but I'm gonna read it. And I found, because like I was able to do all of these, which are everything up here only intersects front.
yeah.
And I was able to do both of them. like locked together. Really do. They don't even tell me this is fair. But it doesn't like tell me.
Wait, what's the difference between main and trunk?
So the trunk is, the main is this main. I. So my main would be like,
Okay.
like that's main,
Uh-huh.
and the trunk's just this.
Okay, okay. Are you able to lock them individually?
Yeah.
Just lock them in?
Yeah.
Let me see that. Let me just see them lock for the main. Oh, it's done. Or I think it's done. Yeah, it's done. That huge, it's still running on my laptop, only 20%.
It's like the whole.
Okay, okay. Can you get a mesh on just the main?
I was not necessarily both the same. It's trying to get my model to the lot.
Yeah.
So I have one previous. I missed like.
Okay, so you're gonna click
Oh, it's
on,
using.
okay, so
Is that when you go to put graded?
yeah, so go ahead and delete that one.
Let's take that. in.
Yeah, yes. Okay, so next we need to put estimate to choose the mesh size.
Who's that? Which one is one?
That's fine. Okay, go ahead and put them on, run the measure. Good. Usually if the measure fails, you okay, it's not a bad start. But then, yeah, we need to get the other customers.
And you were saying something, you can't like. Buy them, sessions.
No.
Yeah.
You need to all be one model for the mesh. Okay, so let's see, so then there's an issue when you try to combine the name.
It did give me the one, like, so if you try to model say like this.
Yeah.
And it's not touching anything, will it give you that partially intersected there?
So the.
Because when I did mesh all my other, like I meshed all the other segments except for the main ones.
Yeah.
And it was able to mesh all of it, or I was able, it was not to mesh, it was able to just swap them together.
Yeah, yeah.
It did give me like a partial intersection. Partial intersecting me.
Yeah, I think I remember I tried mopping all of this together once. Maybe that,
Oh, like during the grade.
yeah.
Yeah, it wouldn't have sense. That's
It's.
I do have a feeling it has to do with that first segment in the phone. I don't want it per se, but.
I mean, by itself, this looks fine.
When I used to do this too.
Good. Oh.
Oh, I did,
This first segmentation.
I did, I changed the segment.
Oh, okay.
I like made it smaller, I thought. Because initially I did have like the segments like intersecting a little.
Yeah.
So
I think that was the issue before. I think it was so big. I think we just had to. I think a lot of people don't have that. There should be, I mean, this vessel about self loss, this vessel about self loss.
You do main and so.
So it hasn't been funny. And a solo by itself.
Oh, the main like. I go to create model. Maybe because,
Is it?
yeah,
It doesn't look like it's still.
yeah,
It's probably this transitions like between kind of things that you might be wrong with religion.
yeah. So I would maybe,
Shrink that.
I maybe move it. I think these ones are okay. I think this one, because like you can see that it's,
Yeah, it's having a shoot.
oh, okay, I see. Yeah, because this, so you can see here that the gap between the two is very large. This is really small. So it looks like just because the path, I think got like a little bit kind of skewed. So I think just this segmentation moves like this.
Yeah,
So I would maybe delete this segmentation and refine the window.
so it's a little more normal.
Exactly, yeah.
Okay.
I think that's probably the
Okay,
issue.
that's what I'll start with. Yeah, I'm still in class, but I'm coming on. Are you guys in E21? Are you in E21? Alright.